Hello students, I am Vishwanath. Welcome to my YouTube channel. Today I am going to discuss about Ampere's circuital law and its application. First statement: the line integral of the induced magnetic field, that is B vector, in a closed loop is equal to the mu0 times of the algebraic sum of the current passing through that closed loop. That is, let us consider this is a closed loop and this closed loop is denoted by L. Okay, and I draw it with the blue line, and this black line indicates the direction of the flow of current. Okay, I1, I2 and I3 pass through this closed loop L. P be a point on this line. Let the induced magnetic field B vector is on the P, that is the induced magnetic field strength at the point P is B. Now closed integration of B dot dl, that is line integral of closed line integral of B vector, is equal to mu0 into algebraic sum of the current I1, I2 and I3 and so on. Okay, since I1 and I2 move in the forward direction, that's why I1 plus I2, and I3 move in opposite direction, that's why it is minus I3. Okay, this is known as Ampere's circuital law. Next, the application of Ampere's circuital law. First, determination of induced magnetic field B vector due to a long straight current carrying conductor at a point outside the wire. That is, let this is a current carrying conductor which is infinitely extended, that is very long, and I amount of current is passes through it. You already know that about the direction of lines of force produced due to the infinitely long extent current carrying wire or current carrying conductor. That is, when the current moves in upward direction, then according to Maxwell's right hand corkscrew rule, the magnetic lines of force is rotate direction of the magnetic lines of force in anti-clockwise direction. Okay, it is shown in the figure. Now let us consider it is a circle having radius r. O is the point of this circle. P be a point on the circumference of the circle. B, capital B vector, is the induced magnetic field at the point P, which is produced due to the current carrying conductor. Okay, now you already know that the tangent at the point P and B vector are parallel to each other. That is, the direction of dl vector and B vector are parallel to each other. Now applying Ampere's circuital law, we can write that closed integration of B dot dl is equal to mu0 into I, where mu0 is the magnetic permeability in air or vacuum. You know that the intensity of induced magnetic field, that is B, is a function of R, that is the distance between the O and P. Since R remain constant, then the value of magnitude of B also remain constant. That is, the magnitude of B is remain constant on every point on the circumference of the circle. That's why we can introduce B outside the integration. Therefore, B into closed integration of dl is equal to mu 0 into I. Since B vector is parallel to dl vector and magnitude of B remains constant when R is also remains constant. Closed integration of dl is equal to the circumference of the circle, that is 2 pi r. Therefore, B is equal to mu 0 by 2 pi I into r. This is the magnitude of the B vector, or this is the magnitude of the intensity of induced magnetic field at the point P due to the current carrying wire. Now, the point P is inside the wire. Okay. So, we are to find out the magnetic field, induced magnetic field at the point P. Let capital R be the radius of the wire. Therefore, current density J is equal to total current I by area of cross section of the wire, that is I by pi capital R square. Now, the point P is inside the wire at a distance small r from the axis of the wire, that is OP is equal to small r. Okay, where O is a point on the axis of the wire. Let us consider small I amount of current is passing through the circle having radius OP. Now, small I is equal to pi r square into J. This gives small I is equal to small r square I by capital R square. Now, applying Ampere's circuital law to this circular loop, we have closed integration B dot dl is equal to mu 0 into I. Similarly, we can get B into 2 pi small r is equal to mu 0 small r square capital I by capital R square. This gives B is equal to mu 0 by 2 pi capital I by R square into small I. That is, inside the current carrying wire, the induced magnetic field is directly proportional to the distance small r. And outside the wire, the B vector or magnitude of B vector is inversely proportional to the distance small r. This graph shows the variation between the induced magnetic field B vector, magnitude of induced magnetic field B vector, and the distance of a point from the axis of the wire. Okay. Along y-axis we draw the magnitude of B vector, and along x-axis we draw the distance, that is small r, from the axis of the wire. Inside the wire, B is directly proportional to small r. That is, the graph is straight line when small r less than capital R, where capital R is the radius of the wire. When small r is equal to capital R, that is on the surface of the wire, the magnitude of capital B will be maximum, and after that the value of or magnitude of B decreases with R. That is, B is inversely proportional to R when small r is greater than capital R. Now, Another and very important application of Ampere circuital law. Determination of induced magnetic field strength at a point on the axis of a long solenoid. Let us consider it is a very long solenoid. Okay. B be the induced magnetic field strength at the point on the axis of a solenoid. Here, this point is well inside the solenoid. That is, this point is not the end point of the solenoid. Let small n be the number of turns of the solenoid per unit length. Okay. N be the number of turns of the solenoid per unit length. Okay. Per unit length. I be the amount of current passes through each turn of the solenoid. B be the induced magnetic field strength at a point on the axis of the solenoid. Now let PQRS is a rectangle where length of PQ or RS is small l and PQ is on the axis of the solenoid. Now applying Ampere circuital law to this rectangle, we have closed integration of B dot dl is equal to mu 0 into total current passing through this rectangle. Now we can differentiate this integration into 4 segments, that is integration of B dot dl along PQ, now integration of B dot dl along QPR plus integration of B dot dl along RS plus integration of B dot dl along SP is equal to mu 0 NIL, because the number of turns per unit number of turns carries I amount of current and total number of turns in the PQ segment is N into L. Therefore, total current passing through the rectangle is NIL. Now, integration of B dot dl is equal to B into L for the length PQ, since the direction of PQ and B are same and the magnitude of B is constant throughout PQ. That's why integration of B dot dl is along PQ is B dot L. Now B dot dl along QR is 0. Since direction of B and PQ are same and B is constant throughout the line PQ, that's why integration of B dot dl along PQ is equal to B dot L. Now along the line QR, the B vector and QR vector are 90 degree to each other. That's why dot product of B dot dl is equal to 0. The dot product of B dot dl is equal to 0. Again, the distance between PQ and RS is very high. That is, the RS is very away from the solenoid. That's why the magnitude of B on the line RS is very small. We can neglect the magnitude of B on RS. Therefore, the integration of B dot dl along RS will be also 0. And the B vector and SP is 90 degree to each other. That's why B dot dl is also equal to 0. Therefore, B dot L is equal to mu 0 NIL. This gives B is equal to mu 0 NI. This is the expression of induced magnetic field strength at a point on the axis of a solenoid. Next, the determination of induced magnetic field strength at an axial point of a toroidal solenoid. Let us consider it is a toroidal solenoid having radius small r and O is the center of it. I current is passing through each turn of the toroid. Okay. Number of turns per unit length of the toroid is small n. Now I am applying circuital law, Ampere circuital law. We have closed integration of B dot dl is equal to mu 0 into total current in this closed loop. Mu 0 into small I is the current passing through small n into total number of turns, that is n into 2 pi r. 2 pi r is the circumference of this toroid. N is the number of turns per unit length. Therefore, here I into n into 2 pi r is the total current passing through this toroid. Okay. That 2 pi r is the circumference of the toroid and n is the number of turns per unit length. This gives B into closed integration of dl. Since the direction of B is along to the tangent of the toroid, that's why B vector and dl vector are parallel to each other, and magnitude of B is constant throughout the circumference. That's why B into closed integration of dl is equal to mu 0 a 9 into 2 pi r, or B dot 2 pi r is equal to mu 0 a 9 into 2 pi r. Cancelling 2 pi r on both sides, we have B is equal to mu 0 a 9. This is the magnitude of induced magnetic field at a point on the circumference of the toroid. This is the end of our discussion, and thank you for watching my video. Have a nice day.